Thanks a lot. As everybody else, we're excited to be here. And so I'll present a recent joint work with Alex Dunlap and Tomasz Komorowski. Alex is in the audience. So, okay, so this is a problem we'll look at. This is a KPZ equation, which was written down many years ago by physicists. So it's this Jacobi equation, and Xi here is a random perturbation. So it's supposed to be maybe Z default model, one of the most important models of surface growth subject to random perturbation. So Jacobi equation was simplest. So the goal, of course, is to study the large scale behavior of this H. Of course, with physicists wrote down this equation, they assume Xi is space-time white noise, so it's generalized Gaussian field with direct correlation. So you know that in d equal to 1, this is only a formal way of writing down this equation. In 1D, at least people know what should be true. So if you assume Xi decorrelates sufficiently rapidly, like in Scott's talk, if it's finite range dependence, then you should have this convergence to the so-called KPZ fixed point. So under this 1, 2, 3 scaling, so you see that you have epsilon function for H, so that's really epsilon to 1. You have 1, 2, 3 scaling, then after centering, so I'm only look at the random fluctuations of this surface. So that should convert to something called the KPZ fixed point, which is supposed to be the universal limit in this universality class. So in particular, for this equation d equal to 1, when Xi is space-time white noise, this result was proved. Okay, so it's almost 2 years ago by Schwarz-Carr and Jerome Costel, and at the same time by Berlin Vierock. So they show that in some sense this center type function after this 1, 2, 3 scaling will converge. So so the scaling here is very special. It tells you that when t is very large, the size of the fluctuation is t to the 1/3. You have 1 and 3 there, and the critical length scale is t to the 2/3. You have 3 and 2 there. So okay. So our goal is to try to have some understanding of the scaling here. I'll not say anything about the KPZ fixed point. Will not be that ambitious. Okay, so before talking about the main result, I'd like to say something about the invariant measure for the KPZ equation, for the Burger's equation d equal to 1. So if you look at this equation, on the right-hand side, it only depends on the gradient of H, meaning that if you add the constant to H, then okay, it doesn't change anything on the right-hand side. So from this perspective, you should not expect H itself to convert to any stationary state because the height doesn't feel the dynamics. It's only the shape of the height that feels dynamics. Okay, that's what I just said. So the evolution of the height only depends on the increment process. So I just look at HTX minus HT0. I call this the increment process, or it's equivalent with the gradient of it. Okay, so the gradient of H solves the Burger's equation with the random forcing, and it turns out that this Burger's equation has an invariant measure. So when Xi is space-time white noise, okay, the good thing about space-time white noise is that in this case, the invariant measure is very explicit. So for the Burger's equation, the invariant measure is the spatial white noise, and for the KPZ, okay, if you integrate the spatial white noise, two-sided bond motion. So meaning that, let me use a board because I think this is important here. Okay, did I switch? Okay. So if my H0x is a Bx, which is a two-sided bond motion, then I run this equation when Xi is space-time white noise in d equal to 1. Then my HTX minus HT0 for any given t, this is a process. It also has the same law as a two-sided bond motion. Okay, so that's what this invariant measure means for the KPZ equation. So if you start from a two-sided bond motion, then you let the surface evolve, then you center the surface, but this random variable is still a two-sided. So you'll see this becomes very important if you want to understand the scale. So that's on the whole line. So on the torus, so I'll stay on the torus. So on the torus, it turns out the invariant measure for the KPZ equation is a bond bridge. So it's the same thing. If I start the equation from, let's say B is a boundary bridge, so on the torus, say 0L.
So your torus is really a circle.
It's a circle, yes. I call it torus, yes. So yeah, because I'll go to high dimensions as well. So if I start the H from a boundary bridge, then for any t greater than 0, it's also a boundary bridge. Okay? But it's correlating in a very complicated way. But I'll decompose the height into 2 parts. So if you look at the height function, I'll decompose into 2 parts. One is that I look at the height at one particular point, which I choose to be 0. The other is this increment process. Okay? So I'll call HT0 absolute fluctuation, and this increment process, the relative fluctuation. So you can just imagine that you stand at x equal to 0, then if you move with the interface, then this relative fluctuation, the HTx minus HT0 is what you observe. So we'll see that the critical length scale, this magical 2/3 and 1/3 actually comes from. Okay, one way to interpret that is a balance of those two terms. So let's first look at what happened on a fixed torus. So now L is fixed. So I look at this equation in D equal to 1, and let's just see a precise space-time white noise. So in that case, it's known that it's a singular as PDE. So it's just a very formal way of writing down this. There's just no such equation in D equal to 1. But if you do this Hopf transformation, you get U, and you solve this stochastic equation with multiplicative noise, and this equation can be made sense by physical method. And you can show that U is strictly positive, so you can take log. And turns out that log of U is the solution to this KPZ equation. Okay, so you can make sense of this KPZ equation in different ways, and it's the same as log of U. So we'll just work with. So I start my SHE, I start my stochastic equation from arbitrary measure of the torus. So okay, so here's the first main result. So on the fixed torus, L is fixed. I can find two positive constants, which I call gamma and sigma, such that if I look at any fixed point on the torus, I have this synchronimity theory. So this surface has a average growth speed, which is this gamma. And if I center the surface, I do this square root T scaling, I get a Gaussian fluctuation. So if you compare this with the result I presented in the first slide, you see that on the whole line, the standard deviation is T to the 1/3. But now I have T to the square root T. Okay? So this is the first difference. The second difference is that here I have Gaussian fluctuation, but yes.
Your interface is going down?
Yes, because, okay, so that's a good point. So because here, that's not the equation, right? I mean, if you really want to write on the formal KPZ equation, you have to subtract infinity. Yeah, so you have this kind of itostructural which fraction which equal to infinity. That's why you have, yeah. Okay, so that's the first difference. The scaling is different, and the second difference is that okay, you have CLT here, you have Gaussian fluctuation here. There you have the fixed point, and the marginal distribution of the fixed point is related to those random matrix theory. So the third difference is that here, this initial data is being completely washed away, because the sigma here has nothing to do with the initial data. But if you look at what happened on the whole line, the KPZ fixed points Markov process, so that depends on the initial data, depends on where you start. So I mean, it's not surprising because on the torus, things mixes fast. So okay, so it's not only on the circle. Okay, so we can do the whole thing indeed on the torus. Okay, in high dimension, we have the same result. Noise. Of course, in high dimensions, we are not expected to make sense of this KPZ, and so we just assume that the noise is white in time, smooth in space. So the same result holds in high dimension, in any dimension. So okay, so the theorem I presented there is for a fixed point x. Okay, so you can ask, okay, what happens to the surface as a random function? So it turns out that this relative fluctuation, which I call this increment process, and as explained, it has invariant measure, and we can show that on the fixed torus, it converges exponentially fast to the invariant measure. In particular, in D equal to 1 for space-time white noise, the invariant measure on the torus is a boundary bridge. So we show that this converges exponentially fast to the boundary bridge. To give you a relatively complete picture of what happened on the fixed torus. So at x equal to 0, you have this square root T fluctuation, and but if you put yourself, if you move yourself with the interface, you see something of order 1. You see something like a boundary bridge. Of course, I mean in high dimensions, it's also invariant measure, but we don't know what the invariant measure is. Why Gaussian here? Okay, so as I mentioned, it's on the torus, so something has a spectral gap. So you have exponentially fast mixing, and okay, so one way to try to understand this is you look at this nonlinear term. So this grad H solves the Burger's equation, and as you can imagine that this thing converges exponentially fast to the invariant measure. Then if you look at your H, that's basically a time integral of this nonlinear term plus a time integral of the noise. So if this thing is very fast mixing time, so if you then look at the time integral is like sum of almost independent random variable. That's why you get Gaussian behavior. Now we have a regular understanding on what happened on the fixed torus. And some other people have very good understanding on what happened on the whole line. So the idea is to try to enlarge your torus and to see whether we can observe some transition, and to try to see how to interpret those two magical exponents. Here's some notation. So I'll use H to denote the solution to the KPZ on the whole line, and HL the solution to the KPZ on the torus of size L. So that's what we proved. So the variance of HL is of order T, so it grows linearly in time. But on the whole line, you know that the variance is okay. So this is the size of fluctuation, the standard deviation, but the variance is 2/3. Okay, so square that. So so this is much smaller than T. So if nothing weird happens, you should imagine that as L go to infinity, your sigma square should go to 0. You should go from T to, you should go to linear growth. You should go from linear growth to sublinear growth. So the diffusion constant should decay. Okay, it turns out that the decay rate is related to those two exponents. Okay, so so for fixed L, as I mentioned, if you move with the interface, then this is what you observe, this increment process. So it converges to stationarity, and we know that in d equal to 1 for space-time Winoid, that's a Born bridge. So if you look at a Born bridge on the torus of size L, you can compute the variance of this Born bridge. That's of order L. Okay? So the variance of so this relative fluctuation, you can view it as a width of this interface. It's just how wide this surface is. So on the torus size L, the variance is order L. So then the idea is that if you just look at H at 0, that's of order T, the variance of order T, but the relative fluctuation is of order L. So when L is fixed, that's much smaller than T. Okay? So so if you enlarge your torus, say at one fixed point, say x equal to 0, this is your variance, and the variance of this increment process is of order L. If L is much smaller than this, then basically it's still a one-dimensional thing, because if you look at two points, let's say HT0 and HTX, and if you try to compute the correlation, you can write HTX as HT0 plus this increment. And basically, this L much smaller than T sigma L squared is the same as saying that this part is much smaller than this part in terms of the variance. So if the difference here is negligible, then when you are computing the correlation is 1, right? So then you keep increasing the torus. So when L is getting larger and larger, if they are of the same order, then you start seeing non-trivial correlations. Okay? So that's a heuristic here. So if you have L of order 1, then the correlation is basically 1 when T is large. So you start increase L, then the relative fluctuation is increasing, and when it's of the same order as absolute fluctuation, then you start seeing non-trivial correlations. So that's a heuristic here. Okay, so that's what I just said. So the variance of this relative fluctuation, when it's of the same order as the variance of absolute fluctuation. Okay, so we're not the first one to come up with this heuristics. So actually, for a different model in this universality class, which is called the TASAP, totally asymmetric simple solution process. So in this paper, I think Bernard was here last week. So okay, this already described the heuristics here. So we'll show that the decay rate of this sigma L squared is 1 over square root of L. And then if you just match terms, you just get L is of order T to the 2/3. You plug that in, you get the variance order T to the 2/3. So the standard deviation is order T to the 1/3. So that's the heuristics of the 2/3 and 1/3. And of course, you can ask me, okay, so where does this come from? So we don't know. Okay, we did some calculation, and okay, so we proved this. But the point is that okay, it's much easier to prove centrometer theory than proving convergence to KPZ fixed point. So maybe you have 10 different ways of proving centrometer theory, and maybe once the proofs will give you some sigma squared that is explicit enough, so you can do asymptotics. So that's what we did. Okay, so we found a proof of a centrometer theory that that gave us some sigma square, and we prove this. And this decay rate is expected to be universal. So for all models in the universality class, you should have this decay rates that give you this critical length scale.
Could you tell us which proof of the central limit theorem that was that gave you?
I'll show you the sigma square. Yeah. So the heuristic might apply to high dimensions. I don't know. It's possible. That's why I use mine. Because nothing is known in high. Okay, so I forgot mentioning that in d equal to 1, almost everything. Okay, so what should be true is null, but in d equal to 2, nothing is null. Okay. The exponents are normal.
Can't you do a numerics to that?
Yeah, you can, but there's no conjectural value, like 1/4 or something. Okay, so yeah, there are numerics, but there's no, yeah.
How fragile is this if you change it slightly from white noise? Like keep the asymptotic fine scale structure the same as white noise.
Yeah, that's what we want to do. We don't know how to do that. So the key thing here is that for white noise, you have invariant measure, you have explicit invariant measure. That's very important. So okay, so I mentioned this. That's the forward-facing part. So this increment process, right? So when t is very large, you know it's a boundary bridge, so you can compute that. But in the general case, it's extremely difficult to study how large this term is. So I mentioned that. Okay, so I haven't presented the main result yet. That's pretty much all I want to say. So that's the main result. So we try to make the heuristic rigorous, and that's what we can do now. So we start the KPZ equation on one-dimensional torus, precise space-time white noise. We start at stationarity, so that's important. And I'm assuming L is order t to the alpha. So okay, alpha is some fixed parameter, and lambda is some fixed parameter. So when alpha is strictly smaller than 2/3, okay, so we have this this variance, right? So that's basically t divided by square root L. So if L is t to the alpha, then it's I think there. So that's a super relaxation regime. So when L is still much smaller than the critical length. Okay. So in the relaxation regime, which is when L is order t to alpha, we can do part of the relaxation regime. So lambda is small. But okay. So the picture here should be. So this is only a partial result. So if you assume, okay, so L is of order t to the alpha. If you assume that this thing is t to the beta, then let's say I draw a picture. This is alpha. This is beta. So when alpha is 0, beta should be 1 because that's diffusive, the variance of order t. Then when you keep increasing alpha, the critical value is 2/3. So you have this linear decay. So this point is 2/3. This is 1 here, right? So and if you choose alpha, this is larger than 2/3, then your dynamics doesn't fill the boundary, right? So it's as if you're on the whole line. So then it's a flat line here. So that's a picture that should be true. So what we proved is this line here and the small part of this point. This is what I just explained. Okay, so for other models, there are more precise results. Okay, so we look at this equation, but there are other models where people can do much more. So what's a heuristic? Okay, I think I explained the heuristics. Okay, how to make it rigorous? So as I mentioned, you should have a reasonable expression of this sigma squared, which shouldn't involve something called the corrector. Okay, so actually it's a homogenization result, like convergence to. I mean, this intermediate theory is a homogenization results. And the first proof I have with Tomasz is to express the sigma squared terms of corrector. But I can do nothing with the corrector, so we come up with a different proof. Okay, so then you show the decay, but we cannot send t to infinity first. So if you want to get the sigma squared, you want to send t to infinity first. But here, I mean, t and L goes to infinity at the same time, so you cannot send t to infinity first, then L to infinity. So you decrease type of stationarity so that you can compute the variance for fixed TIL. Okay, let me go back the formula for the sigma square. That's sigma square. So B here, B1, B2, B3 are boundary bridging, independent boundary bridges. And you can imagine why boundary bridge should show up because that's in one measure, and that's a sigma square. So at the beginning, we saw that okay, it only involves boundary bridge, and you should know everything about the boundary bridge. But this turns out to be okay. To show the decay here is the most difficult part of the paper, actually. So the rest of the paper is like 5 pages. This one is 25. So, so there's a early result Marquior, which give you the explicit density of random variables of the form e to the b integrate. But we have correlated boundary bridges. So we don't know how to use that result. Okay, so as I mentioned, it's 25 pages, so it's pretty complicated. But there's an explicit value of sigma squared that is conjectured by the red-path method. So
how do you prove it takes that form?
How do I prove? Okay, so it's hard to explain. Yeah, so it's we use something called the Clark-O'Connor formula. So so the idea is to write this ht0 minus the expansion of ht0 as an atonal integral. So okay, so that's accomplished by the Clark-O'Connor formula. So in the first proof we had is to do a semi-mathematical decomposition. So for by that we need to solve some corrector problem, basically, and that involves a corrector. So the sigma square involves a corrector, but we don't know how to study the corrector there. So somehow this Clark-O'Connor formula relates the height function with the direct polymer, and the direct polymer on the torus, since your KPZ has invariant measure given by the boundary bridge, the direct polymer has invariant measure given by something related to the boundary bridge, which is something like that. So it's really the special structure of the problem.
So you're taking the value of that derivative without any variables, and then you're integrating against the right question.
Integrating against the white noise.
Right.
Yeah, yes. Turns out that this integrand here, so you have integrand, you have white noise, dy ds. This thing here is related to the density of the direct polymer. And I know the stationary density of the direct polymer, the stationary state of the direct polymer on the torus. So, okay, to answer Scott's question, so so in the homogenization proof, basically you have some additive functional of some macro process, then you solve the corrector equation, right? But here, what we did is to write that additive functional as an atonal integral. Okay, we can talk more about this later. So, okay, so this is the forward-facing part, so work to be done. So, okay, so in high dimensions, we have a Gaussian fluctuation for fixed L for any given torus. And we also know that this increment process converges exponentially fast to stationarity. But we know almost nothing about the stationary state in high dimensions and nothing about the exponent. So the same argument will give us the same decomposition. Okay, so X here in some sense represents the absolute fluctuation, and I can compute that. So that's T sigma square. And Y there is related to the relative fluctuation. So our approach will write this X and Y explicit in terms of the invariant measure. So if you tell me everything about the invariant measure in high dimensions, then maybe I can compute how large this X is and how large this Y is. And maybe by balancing those two terms, I can find the exponent. So everything reduces to the stationary state. So it's not a dynamical problem anymore, it's a static problem. Okay, so another work to be done. So okay, so you see that the stationary state, okay, the stationary solution to this type of HGV equation is closely related to homogenization. And we have many experts on homogenization of this here. So in D equal to 1, the existence and the uniqueness of stationary solution is already highly non-trivial. And here I listed. So a question is to study this. Okay, so you look at the stationary solution, then you ask yourself, what's the size of this increment process? And there's a conjecture here which is consistent with this one. So you see that when size is a space-time white noise, you know the invariant measure is precisely a two-sided bound motion. And if your size is not space-time white noise, if it's some noise that decorrelates sufficiently rapidly, then okay, it's not exactly two-sided bound motion, but on large scales, okay, maybe it looks like that. Yeah.
But what if what if the fine scale is still
the fine scale is what do you mean by the fine scale?
It's like like the kind of you had large scale still fluctuate.
Yeah, the small scale. I mean the small. Okay, I think it's a different problem because if you assume the noise is smooth in space, then okay, HTX is
still rough in space. I just don't want it white noise.
Okay, so there are some other work to be done. Okay, so we prove the centromere theory for fixed L. Okay, so but you're expecting that in the super relaxation regime, which is when L is still much, much smaller than T to the 2/3, you also have streaming theory. But our proof doesn't work. So that's one thing. Another thing is that you can look at Hamilton-Jacobi equation on the torus with different Hamiltonian. Okay? So not necessarily quadratic. Maybe you also expect a centrometer theory on the fixed torus. Okay, so in high dimensions, okay, a less ambitious goal is to show something like this. So the variance grows sublinearly. Okay, so if you can find some epsilon such that the variance, you can have an upper bound of this form, that would be extremely nice, I think. And the best we have now is this T over log T group. Okay, that's it. Thanks for your attention.
What's up, very nice talk. So any questions?
Which proof of the CLT did you pick in the end?
Oh, so okay, so the first paper we wrote is the corrector approach. Then we started working on this. We realized that we need to come up with a different CLT. So we wrote the second paper. So there are two proofs.
But you said there are 10 proofs and you have to use the right one.
Oh, okay. So I mean, by 10, I mean 2. We only have 2 now. Yeah.
What was like the main difficulty in going from one dimension to like multiple dimensions with white noise?
Yeah. So okay. So it's about making sense of this equation. So when you're concise spacetime white noise, I think give a meaning of the solution to KPZ or SHE is an open problem in D greater than Q2. So, but here actually you don't necessarily want white noise, right? So as long as your potential decorrelates sufficient rapidly, if you expect some universal behavior, then the large scale behavior should be the same. So being white is only the small scale. So here I care about the large scale, yeah. But being white is also good because in D equal to 1, being white, if you have Dirac function, you see that sometimes you can solve things more explicitly when you have Dirac function. So same here in D equal to 1, we have two-sided bound motion as an invariant measure. But if you have a color noise, you also have invariant measure, but you don't know what that is.
I feel like we still haven't answered the question. Which proof? What is the second proof? You told us the number.
Yeah, I said that. It's by this.
Like, what is it using?
It's a Clark-O'Connor formula.
Okay. Okay.
So basically that involves the Malman calculus, and somehow this height function, the Malman calculus also, the Malman derivative of the height function of the noise is directly related to the direct polymer. And yeah.
So that would be, thank you.
Thank you.